Welcome to Study Loop.
Okay, so we're doing chapter 29, problem 29. So in this problem, we have the little bar here, and this is all in a B field that is pointing into the page. And they call this point C, this point D. And along this, there is a bar. And it is moving along at a velocity v in this direction. Okay. It also tells us the length here is 50 centimeters. And magnitude of b is 0.8 Tesla. Okay. So it says, part A, find the magnitude of the EMF induced in the rod when it is moving towards the right with a speed of 7.5 meters per second. So V equals 7.5 meters per second. So we want to use the equation here we've been using, that the EMF is this, and we know that the B field and V are 90 degrees apart, so this is all the equation we need. We don't need to use the sign part. So we know that this is going to give us 7.5 meters per second times 0.8 Tesla times 0.5 meters. This is 3.0 volts. Cool. So now for part B, it says, in what direction does a current flow in the rod? So we know that B is into the page, and as it moves to the right, A gets bigger, right? The area, because this is our loop right here. This is our loop. The A is getting bigger, the B is constant. So that means our flux B is into the page and it's increasing. So using Lenz's law, the induced B must be out of the page. Okay, so now using the right hand rule, does it counterclockwise or clockwise point it out of the page? You do that and you'll find it's counterclockwise. So that means in the rod, if this is moving counterclockwise, it's moving from B to A. Cool. So part C asks if the resistance of the circuit is 1.5 ohms and it's constant, find the force required to keep the rod moving to the right with a constant speed of 7.5 meters per second. Okay, so we can find the current in this circuit now by taking the EMF and dividing by the resistance, and that comes out to being 2.0 amps. Okay, so we also know that to keep this, maintain this constant speed, the force external must be equal and opposite to the magnetic force that is exerted on the rod. Okay, so that's kind of a lot of words. So basically we have to say the external force is equal and opposite this other force on the rod we'll call L. Okay, so the force on L we can calculate because we know this is just a magnetic force on a rod. So this is the current times the length of the rod times the magnetic field strength times sine of the angle between the current and the field, which in this case is 1. So this is 2 amps times 0.5 meters times 0.8 Teslas. And this comes out to being 0.8 newtons. Okay? So that means the external force the magnitude of the external force required to keep this moving is exactly 0.8 newtons, because we want it to be at a constant speed, so they went to 0 net force. Awesome. And this must be in the direction to the right, because FL is in the direction of the left. The current is trying to make this smaller, but we're trying to keep it moving. Awesome. Okay, so now for part D, it says compare the rate at which mechanical work is done by the force. So for mechanical work, this is F times the velocity. This is the rate of mechanical work, and that's going to be 0.8 newtons times 7.5 meters per second. And this comes out to exactly 6.0 watts. And we're going to compare this to the rate at which thermal energy is developed in the circuit. And that is given by I squared R. So that is given by 2 squared times 1.5. And guess what? This is also 6.0 watts. So they're both the same, which is exactly what they need to be. This is required because of conservation of energy. So this whole problem is working out great.